Imagine a city where electricity never goes completely off. The lights stay on, the grid appears to be working, but inside factories, machines fail unexpectedly. Computers crash without warning, motors overheat, trip, or slowly die, and no one really knows why. We usually blame blackouts, but in reality, most power system problems happen while electricity is still on, the voltage is there, but it is not healthy. This is the story of voltage quality problems, the silent, invisible issues that modern power systems struggle with every single day. Let's start with a simple but fundamental question. What does good voltage actually mean? In theory, voltage should be perfectly sinusoidal, constant in magnitude, constant in frequency, symmetrical in three-phase systems. This is the voltage we draw in textbooks. This is the voltage most control and protection systems assume. But in reality, perfect voltage does not exist. Voltage quality refers to how closely real voltage matches its ideal form. The closer it is, the healthier the system. The further it deviates, the more problems we face. When voltage deviates from its ideal behavior, we enter the world of voltage quality problems. In the early days of power systems, loads were mostly linear. Generation was centralized. Control systems were slow but predictable. Motors, lamps, and transformers dominated the grid. Waveforms were relatively clean. Voltage problems were rare and usually localized. If a problem occurred, it stayed in one place and was easy to identify. Then, everything changed. The three revolutions that changed everything. 1. Power electronics everywhere. Rectifiers, inverters, variable speed drives, switched mode power supplies. These devices do not draw current smoothly. They draw pulsed, non-sinusoidal current. And here is the key point. Distorted current creates distorted voltage. Once power electronics entered the grid at scale, voltage quality became a system-wide challenge. 2. Renewable energy integration, solar PV, wind turbines, converter-dominated generation. Modern grids now have less mechanical inertia, faster dynamics, higher sensitivity to disturbances. Voltage is no longer supported by massive synchronous machines alone. It is now maintained by controllers, algorithms, and converters. 3. Complex and sensitive loads. Data centers, EV chargers, industrial automation, modern loads are extremely voltage sensitive, have very low tolerance to deviations. A voltage issue that was acceptable 30 years ago can shut down an entire production line today. Meet the main characters. Types of voltage quality problems. Voltage sag or voltage dip. A short reduction in voltage magnitude caused by short circuit faults, motor starting, large load connection. Impact. PLC resets, drive trips, process interruption. This is the most expensive power quality problem in industry, not because it damages equipment, but because it stops production. Voltage swell. A temporary increase in voltage, often caused by load rejection, fault clearing, danger, insulation stress, accelerated equipment aging. Small, repeated swells slowly destroy equipment without obvious warning. Voltage interruption. A complete loss of voltage, short or long, planned or unplanned, always critical. Even very short interruptions can cause data loss, process failure, safety risks. Voltage harmonics. Voltage waveform distortion due to harmonic currents, closely linked to THD, power electronics, weak grids, effects, transformer overheating, resonance phenomena, protection malfunction. Harmonics turn a clean sine wave into a distorted and dangerous signal. Voltage unbalance. Unequal phase voltages in a three-phase system. Very dangerous for induction motors, rotating machines. A small voltage unbalance can cause a large current unbalance, leading to overheating and torque pulsations. Transients and spikes. Fast, high magnitude voltage changes. Sources. Lightning strikes. Switching operations. Often invisible, until equipment suddenly fails. Why voltage quality problems are so dangerous? Voltage quality problems affect equipment, lifetime, energy losses, process reliability, protection systems, overall grid stability, And here is the key insight. Power systems rarely collapse due to lack of energy, but often due to poor voltage quality. Energy may be available, but if voltage is unhealthy, that energy becomes unusable. How do we solve voltage quality problems? Traditional solutions: capacitor banks, voltage regulators, transformers with tap changes, effective but slow. Modern solutions: fax and power electronics, SVC, STATCOM, DVR, active power filters. These devices react extremely fast, inject or absorb reactive power, restore voltage dynamically. They are the immune system of modern grids, control and monitoring, power quality analyzers, IEC 61000 standards, grid codes. You cannot control what you do not measure. The future of voltage quality. Future grids will be converter dominated, less inertial, more decentralized, which means voltage quality will be harder to maintain. Control strategies will be more critical than hardware. Voltage quality is no longer a secondary issue, it is a core design constraint. So the real question is not why do voltage quality problems exist, but can we afford to ignore them? In modern power systems, voltage quality is not a luxury, it is a requirement for survival. If you understand voltage quality, you understand the hidden dynamics of the grid. And once you see them, you can never unsee them. Thanks for watching. Stay safe and stay curious.